Okay, in this video we're going to start talking about waves. Waves are all around us. Okay, every time you use your remote control, it produces waves that carry signals and can turn your TV on or off and all kinds of things. Every time you speak, you're producing sound waves. You drop a pebble in a pond, that produces waves. The ripples that move through the water in the pond. Electromagnetic radiation is can be understood in the terms of waves. So basically we have waves all around us. So it's important to understand wave phenomena. In this chapter what we'll do is we'll be looking at waves that require a medium for them to propagate. Okay, so these are going to be called mechanical waves. So these require a medium as opposed to electromagnetic waves that do not require a medium. So require a medium. Okay. On the other hand, electromagnetic waves do not require a medium. Okay. This is basically light. Okay. Light can travel through space, empty space, and that that's why we can see stars. That's why we are able to communicate with the satellites that are out there in space, all our GPS satellites, and pretty much a lot of communication happens using electromagnetic waves. So we have in this chapter we look at mechanical waves. Now the examples of mechanical waves for us will be the waves that are produced in a string. If you were to attach a string to a wall, and if you were to say disturb the string, you could produce a wave that would travel through the string. Okay. On the other hand, another kind of mechanical wave would be the wave produced by sound. And what happens is, as you make as a sound is created, it leads to pressure variation in the air. Okay, so at some points there's high pressure area, so this is a high pressure area, then you have a low pressure area, and then you have another very high pressure area, and then a low pressure area, and then high pressure area, and so on and so forth. And once again, this requires a medium. Okay, now I've drawn these two different waves, and one of the reasons is that if you look at the string, the waves in the string, the particles in the string, they move in a direction perpendicular to the direction of the wave, and we call such waves transverse waves. Okay, as opposed to the waves that are produced by sound, or also if you were to take a slinky, for instance, if you were to pump a slinky from one side, you can see that the particles of the medium, okay, travel in a direction parallel with the direction of the wave. So such waves are called longitudinal waves. Okay, so we have transverse as well as longitudinal waves. Now, it's not that every wave has to be either a transverse or a longitudinal wave. There are times when waves will be both. In case of an earthquake, the wave that travels is going to be both longitudinal as well as transverse. The waves in water are going to be both longitudinal as well as transverse. Okay. Now the good thing is that whether it's longitudinal or transverse, we can represent the wave simply by a sine or a cosine function. So in this case, what we'll do is we'll use a sine function. If our wave, let's say, were to start at some point and would propagate. Now, as opposed to what we drew in the case of, say, a simple harmonic oscillator. Okay. What you see here is actually a wave in space. Like you'll be looking at a wave, and if you were to say take a string and move it up and down, it produces a wave in the string, and say at any instant of time, this would be what you would actually physically see. Okay, so this would be a snapshot at any instant of time. At another instant of time, for instance, the wave may look, it may end up looking something completely different. It may end up looking like it has a profile of this sort. Okay, but those would be at different snapshots. At any instant of time, we have a wave that basically has this appearance. Okay, now every wave for a wave of this sort, what we can do is, if it's a transverse wave, we have a crest and a trough. Okay, and then we also have an important characteristic of the wave, which is called the wavelength, which is the distance between any two crests or any two troughs. Okay, the wavelength is represented by the Greek letter lambda. Now, in the case of a longitudinal wave, okay, once again we can represent a longitudinal wave also with the same thing. And what we'll do is, if I were to say have a longitudinal wave, the parts of the crest would be the high pressure area, okay, and then the part of the wherever you have the troughs would be the low pressure area, and once again the high pressure here, and then the low pressure for the troughs. Okay, now for longitudinal waves, the high pressure areas are called compressions, okay, and the low pressure areas are called rarefactions. Okay, and once again you see that we can represent the wave in the same way, and the distance between two compressions or two rarefactions is simply going to be your wavelength. All right, so this is how we'll represent a wave. A wave is going to have a few characteristics such as the frequency, and because a wave repeats itself, we can also have a time period, and we can combine the two things to define the speed of the wave, which is going to be the wavelength divided by the time period, or more importantly, we'll write it as wavelength times the frequency. Okay, so this is a very important expression, and we'll keep going back to this one. Now, on the other hand, we can also write the equation for the wave in space. Now, if you remember what we wrote down for a simple harmonic oscillator, our x was simply given as a cosine of omega times t. But this is when x simply changed from one position to another. All right, so it was just the oscillation in say a horizontal direction or a vertical direction. Okay. On the other hand, in this case right now, what we have is not only is our wave changing in time, but it's also changing spatially. Okay, so what we'll do is we'll write, the best way to write this wave is in this form: a sine of k times x minus omega times t. Okay, and I'll explain each of the terms here. The y is the y position of the wave at any instant of time. K is equal to 2 pi divided by lambda, and what is going on here? And omega, you may remember, is 2 pi over t. Okay, so we can write the wave as either a sine of 2 pi times x over lambda minus t over capital T. Okay, so this would be one way of writing the equation for the wave. Now we're going to leave this equation for now, but later on when we study how waves combine with each other, we'll come back to this equation to look at what the conditions may be to get certain kinds of whether constructive or destructive interferences. All right, so this is basically the equation for the wave itself. So y is equal to a sine 2 pi x over lambda minus t over capital T. A wave has a few characteristics. It has a frequency, it has a wavelength, and we can relate the speed to the frequency and the wavelength in this form. Okay, and like I said, we also have two kinds of waves: longitudinal wave and transverse wave. In the next video, we'll look at the speed of wave through a string, and then in future ones we'll also look at interference of waves and also wave reflection. All right.